Lesson 11 is called Interpreting Functions, and a big part of this lesson is learning how to compare linear and exponential functions. So the formula for linear functions is f of x or y equals mx plus b, where b is the starting value. On a graph, it would be the y-intercept. And m is the rate of change, or you may see like the word slope used to describe that. And then if m is positive, that means that the function would be increasing, so like kind of gaining value overall. And if m is negative, that means the function would be decreasing or losing value. So for example, like if you are making like $10 per hour, you would have a positive rate of change of like $10 per every 1 hour. Versus if you spend $10 a week, you would have a negative rate of change. If you're talking in terms of like your bank account, it would be going down that same amount per week. So we use linear functions to represent when a value is increasing or decreasing by a fixed amount. So anytime there is a consistent rate of change or a consistent just like slope or just change overall, that would be something that's linear. So like if you drive for 2 hours at 55 miles per hour the whole time, like you're on cruise control, that would be a linear function. For exponential functions, the formula is, or at least one of the formulas is f of x equals a times b to the x. You can also choose to use the exponential growth or decay formulas depending on the situation. But that f of x equals a times b to the x, that's like our kind of like standard general form for an exponential. And in this case, a is the starting value. So the number out in front, that's where we start at. Or like if it was a sequence, it would be a1. If you are, say, like starting with a population of like 1 million, that would be A. And then B is the growth factor. So that's like how much is that value changing by over time? Is it like doubling or tripling or getting cut in half or increasing by 5% or so on? Those are just a couple of different examples. If b is greater than 1, that would mean that the function is increasing or its growth. If b is between 0 and 1, it would be decay or decreasing. When b is between 0 and 1, that would look like a like decimal or a fraction like 1/2 or like 0.3. And then we use exponential functions to represent when a value is increasing or decreasing by like an exponential rate. And what that looks like is either it can be increasing or decreasing really quickly a lot of the time. When you're looking at the actual values, though, it would be you are like multiplying by a consistent number each time to get to the next value in your function. So like, say if you're doubling, you'd be multiplying by 2, or tripling, you'd be multiplying by 3, or like cutting things in half, you'd be multiplying by a half. But exponential functions would be multiplication versus with linear functions, if you're looking at the like kind of change between the values, that would look more like addition or subtraction. And then just to kind of compare this back to like a previous lesson, we learned about sequences, and we learned about arithmetic sequences, and that was when you added or subtracted a number each time. Arithmetic sequences kind of go with like linear functions where it's a consistent rate of change. So like, for example, if I had a sequence that was like 7, 10, 13, 16, and so on, each time I am adding 3, no matter what, I'm adding 3, adding 3, so the consistent rate of change, and I could technically write a linear function that was just like that sequence. Versus for exponential functions, you are kind of like multiplying each number or by a number each time to get to the next one. So the rate that you are increasing or decreasing by is changing. So like what I mean is, so like let's say I have 2, 6, 18, 54. And so to get from one number to the next, this is like a geometric sequence where we have a common ratio. To get from one number to the next, I am multiplying by 3, and like, yes, that is like a common thing. It's happening each time multiplying by 3, but you'll notice that like the like gap between one number to the next is growing. So like I'm going from 2 to 6, so that gap is 4. 6 to 18, that gap would be like 12. 18 to 54, I don't even want to do the math on what that gap is, but the rate of change is not constant. Like the change in that sequence is like kind of growing over time. It's growing at an exponential rate. Okay, so Moving down to kind of like comparing the graph of exponential growth versus linear growth. Actually, I'm going to jump back to this one in a sec. Just a quick reminder, this little section goes with the exponential growth or exponential functions in general. And it's just kind of a quick reminder that you can also use the exponential growth or decay formulas to write functions for exponential growth, depending on if it makes it easier. We'll see a couple of examples of each, but you want to have those formulas along with this kind of more general formula all written down somewhere for you to refer back to. Okay, and then just quick reminder, the exponential growth formula is f of x equals a times 1 plus r to the x, and the decay one is really similar. It's just f of x equals a times 1 minus r to the x. So really the only difference is for growth, it is 1 plus r, and that's what makes it increase. And for decay, it's 1 minus r, and that's what makes it decrease. So when you're looking at a graph, now I'm back over in this section right here. When you're looking at a graph of linear growth versus exponential growth, linear growth will look like a straight line. There will be no bends or breaks or curves in it at all. Linear will be straight, constant, all those words I can describe, like something that is just staying a consistent rate of change the entire time. And then for exponential growth, you can see that the rate of change is like kind of increasing on this one as we go further along the graph. And what that means is like down here, the rate of change is like a little bit flat almost. And then up here, it's getting like steeper and steeper. And so it's changing, it's not constant. Okay, so exponential growth, you'll see more of like that curve versus linear growth will always be a straight line. And linear actually just means like line. So when you see the word linear and you think graph, you want to think straight line. Okay, so example 1, at the town fair, the cost of admission is $15 and the cost for each ride ticket is $3. Write a function to represent this. So first we have to decide like, okay, well, what type of function is this going to be? Is it linear or is it exponential? And we're asking ourselves really like, is there a consistent rate of change or is our change happening more like an exponential rate? So for example 1, we pay $15 to get into the fair, and then we pay $3 for each ride ticket. So we're paying $15 one time, and then depending on how many rides we go on, we're paying $3, but that $3 is not changing. Every single ride ticket is going to cost $3. That is consistent, so it's a consistent rate of change. So we would want to use the linear function formula. So for linear functions, it's f of x equals mx plus b. And it said up above that b is the starting value and m is the rate of change. So b is the starting value, kind of like how much you're going to pay to get into the fair in this context, and then m is the rate of change. And our function is really just going to represent like how much total money we're going to end up spending. So if we think about, okay, well, we're going to pay $15 for sure to get into the fair. So that's going to be our starting amount that we pay. We're going to pay $15 to get inside. And then depending on how many rides we go on, that's going to be like kind of how we end up at the remaining like total of how much we pay. So each ride ticket is $3, and that's going to be our rate of change because like if we go on one ride, that's going to be like 1 times 3. If we go on 2 rides, that'd be 2 times 3, 3 rides, 3 times 3, and so on. So that $3 is like what the potential change is depending on how many rides we choose. So we're going to take that 15, we're going to put it in for B, we're going to take that 3, we're going to put it in for M, and then that's going to give us our function. So it'd be f of x equals 3x plus 15. And notice like the x stays in the function. That'll kind of always stay there. But what kind of you'll see the pattern with like writing linear functions is the rate of change, especially when we're talking about money, is going to be some sort of reoccurring charge, some charge that happens more than once. In this case, it could be more than one ride, versus B is going to be like kind of a one-time fee. So like another example could be like if you go to a parking garage and you have to pay $10 to get into the parking garage, but then you pay $2 per hour. Well, the $2 is the reoccurring, that would be our rate of change, and the $10 would be what we have to pay just to get in, and that would be our starting amount B. Okay, so we have our function f of x equals 3x plus 15, and then down below that it says how much will you pay if you ride 6 rides. So we took, in our function, we took 3, our rate of change, and we multiplied it by x. So if we did like 1 ride, it would be 3 times 1, or if we did 2 rides, it'd be 3 times 2, and so on. So that must mean that x represents the number of rides that we go on, so we're going to have to put 6 in for x. So the way that we would write that is be f of 6 equals 3, and then instead of like, I have an x in my function here and here, if I'm going to put 6 in for x, I'm going to put it in for both x's. So it'd be 3 times 6 plus 15. And then after that, I would follow order of operations to simplify. So in this problem, I have multiplication and addition. I would need to multiply first before adding. So I do 3 times 6, that's 18. Bring down the plus 15. And then after that, I can add the 18 and the 15. So I would end up with f of 6 equals 18 plus 15, so 33. So what that means is if you ride 6 rides, you will pay $33 total, including the like cost of admission plus the 6 rides that you go on. Okay, so moving on to example 2. A certain type of cell can triple itself every hour because it has a growth factor of 3. A laboratory has 12 of these cells. Write a function to represent this. So if something is tripling, that means it is multiplying by 3 each time. So up here, we actually just like kind of coincidentally ended up with numbers that were tripling. So I was going from like 2 to 6, that's multiplied by 3, 6 to 18, 18 to 54. To get to each new number, I was multiplying by 3. Each number was tripling. And we saw in that example that that was not a consistent rate of change, so we could not use a linear function to represent that. But what we were doing is we're multiplying by 3 each time, and when you're multiplying by a number each time, you can represent it with an exponential function. So we would use the formula for the exponential function, which is this one right here. And this is one where I actually would recommend using that one up top rather than the exponential growth and decay formula, and I'll explain why in a second. So I'm going to start with that formula from up above that was under exponential function. So it's f of x equals a times b to the x power. And up above we kind of wrote like what each thing meant. So we said a was the starting value. So a was the starting value. And then going back up here, b was the growth factor. I'm just looking kind of at this section right here where we had each thing labeled. So b was the growth factor. And then x is just going to be our input. That's going to stay as is. So if we read through the problem one more time, it says that a certain type of cell can triple itself because it has a growth factor of 3. So it says it directly there in the problem, growth factor of 3. So that's going to be B. And then it says the laboratory has 12 of these cells. So that's how much they start with. So we're going to put 12 in for B, or in for, not B, in for A, because A is our starting amount. I know it's kind of funky because B is the like starting amount for linear, but A is the starting amount for exponential, like kind of looking at right here and right here. So that's why you got to like kind of have them on a note card, because it could be so easy to switch them up. But having them on a note card and being able to like refer back to them on like quizzes and exams would just save you a lot of headache. Okay, so A is the starting amount, so it starts with 12 of those cells, so A is going to be 12, and then the growth factor is 3, so we'll put 3 in for B. So it'll be f of x equals 12 for A times 3 for B to the x power. And then that's our final answer for our function as an exponential. So it's f of x equals 12 times 3 to the x. Sometimes people see a problem like this and they want to multiply 12 and 3 together to make it more simplified, which I respect. But technically we can't do that because we would, in order of operations, we would like simplify exponents before multiplication. And since I can't simplify that exponent because it's just an x, that means I can't move forward and simplify the multiplication because I just can't get through the exponent part of it. So we would leave it as is. And then I said I wanted to kind of talk about why I chose this formula as opposed to the exponential growth or decay. And personally, I like whenever you see a word like double or triple, or you're directly given the growth factor like we were here, I think it's a bit easier to use that formula because it has the growth factor exactly in it. Versus problems that I think would be best for like exponential growth or decay is like if they told you that the growth rate was like, I don't know, 5% or something, because in this case, R stands for rate, and like we would be able to put that rate in there and then add it or subtract it from the 1 to be able to get our final growth factor. But when we're given a word like double or triple or half, or we're directly told that the growth factor is 3, it's best to use that like kind of first formula up here because that has growth factor directly in it. Okay, so the second part of example 2 says how many cells will be there after 7 hours. So in our formula kind of represented like any amount of time, but now we have to figure out how much time is going to go by after 7 hours. So in this case, that 7 is going to be x, or really for like any amount of time, it's going to be x. So if you want to find 2 hours, you put 2 in for x, 3 hours, you put 3 in for x, and so on. So we have to take that 7 and put that in for x in the function. So what that would look like is we would find f of 7. And what that means is that wherever there's an x in the function, we put a 7 there, and then we'll simplify. So f of 7 equals 12 times 3, and then raised to the 7th power. And then we have to consider order of operations. So we would simplify exponents first before multiplication. So we would not do 12 times 3 first at all ever. We would do 3 to the 7th power. So I just want to stress that this 7 up here is an exponent, and it will be for any exponential function that'll be an exponent. So that does not mean 3 times 7. It means 3 to the 7th power, which means 3 multiplied by itself 7 times. So you really want to use a calculator for it. I'm going to pull one up. Okay, so this is just the calculator that you get when you type it into Google. I think this is the easiest one to use for a problem like this. So I'm trying to find 12 times 3 to the 7th power, and I have to do 3 to the 7th power first. So it's not 3 times 7. It will never be that because the 7 is an exponent. So on mine, I have to click over to the f of x, but before I do that, I want to type in the 3 first. And then you want to look for the button that has an X with a little Y in the upper right corner. So on mine, it's the bottom row and the third button over. And you can see that pops up a little box, and that little box is for an exponent. So in that little box, I would type a 7. And then that would give me 2,187. So this is going to be 12 times 2,187, and you see like that's a lot different than 21 because it's not 3 times 7, it's 3 times 3 times 3 times 3, 7 times. And then now I can take that 2,187 and I can multiply it by 12. And that would give me 26,244. So f of 7 is 26,244. So that means that if the laboratory starts with 12 cells and it triples every hour, that means that we will end up with after 7 hours, 26,244 cells. So one thing I want to show you really quick is if you do use this calculator, you can technically type in this whole part of the problem all in one step and get the same answer. So I'm going to clear this and just show you really quick. So it'll be 12 times 3, and then I need to get my little exponent, so I'm going to go over and click to the X to the Y button, type in my 7, and then this calculator will follow order of operations. I will say it's really hard to get your phone calculator to do it, so that's why I recommend this one. More often than not, the phone one would do 3 times 7, or sorry, not 3 times 7, 12 times 3 first, and then raise it to the 7th power, which is really hard for them to organize it. But this one, you could see I did 12 times 3 to the 7th, and it followed order of operations, and it gave me the same answer as if we had done it in 2 steps. So you can definitely do that. So for example 3, the price of a cake is based on the number of servings and the initial fee for design and supplies. The following table represents some of the prices for cakes. Write a function to represent this situation. So before we decide how to write the function or what formula to use, we have to determine whether it's linear or exponential. And if we're deciding on linear, we're trying to look for a consistent rate of change. So sometimes on your table, especially if you see the left side of the table just has numbers 1, 2, 3, 4, you can just look at the right side and see if you're adding a consistent amount each time to get to the next number. But in the case of this table, our left side is not going just 1, 2, 3, 4. You can see it goes from 10 to 20 to 40 to 80. So it's kind of changing by various amounts. So there's a little bit different approach that we have to take. And I'm going to refer back to the rate of change formula, which one of the ones that we've talked about is M equals, that's a triangle Y, but that triangle, remember, means change. So change in Y over change in X. I'm just going to leave a little note that triangle just means change. It's I think a Greek symbol that's called delta, and it just is another kind of shorthand for change. So the way that we would check that on this table is if we look at say the change in Y's, I'm going from here to here. I'm going from 35 to 55, so that means I'm going up 20. And for my change in X's, I'm going from 10 to 20, so I would be going up 10. And then from here to here, I'm going from 55 to 95, so I would be going up 40. And if you're not sure how far up you're going, you would do 95 minus 55. You would work backwards, and 95 minus 55 would give you 40. And then over here, I'm going from 20 to 40, so to go from 20 to 40, I'm adding 10. And then to go from 95 to 175, we can do 175 minus 95 to figure out what I would need to add. So 175 minus 95 is 80. So this would be plus 80. And then from here to here, I am going up 40, from 40 to 80. So if we look at our table right now, it doesn't look like it's going up by a consistent amount, but really what's happening on the table is we're kind of skipping numbers in between, because the serving size is not going up consistently. First it goes up by 10, then 20, then 40. So really what we have to do is we have to find a couple different slope formulas and compare them, see if they're all the same each time. So we would take each change from each little section of the table. So the first one was 20 and 10, or 10 and 20, but remember we do the change in Y on top, and the right side of the table is Y, the left side is X. So for this one I would do 20 over 10. So 20 over 10, 20 over 10 simplifies down to 2 because it's just 20 divided by 10. And then for the next section of the table, it would be the 20 and the 40, but again, we put the change in Y on top, so it'd be 40 over 20. So 40 over 20, 40 divided by 20 is 2. And then for the next part of the table, it's 40 and 80. So if we find the slope between, or the rate of change between those two, the change in Y is 80. over the change in x is 40, and then 40 over 80 simplifies down to 2. So even though it didn't look consistent right away, when we compared like the actual rate of change between all those numbers, they all simplified the same way. What was really happening is we were just kind of missing some numbers on the table. So like we didn't go up like from like to 30 right here, or to 50, 60, 70. We missed all those numbers. So that's why some of the jumps seemed a little bit bigger in some parts of the table than others. But since they all simplified to 2, that means they all have a consistent rate of change, and that rate of change m equals 2. So we've proved that it's linear because we got the consistent rate of change each time. So the linear formula is f of x equals mx plus b, and m is going to be our rate of change, which we just found out no matter what kind of like sets of numbers that we pick is 2. So we'll put a 2 in for m. And then b is supposed to be our starting amount, but our starting amount is like what we would charge if we weren't like kind of just to get the, I guess, the initial design. So when you're looking at a starting amount for your table, you really want to go all the way kind of backwards until you would get 0 on the left side of your table. That's going to give you your starting amount. Whatever is like on the right side of that 0 is going to be the actual like b that we put in our table. So like you'll see on the table, like from here to here, I added 10. So if I wanted to go backwards, I could subtract 10. And then I would have to do like this part backwards too. So instead of adding 20, I would subtract 20. So I'd do minus 20. So 35 minus 20 would be 15. So this number right here is going to be my b. That's kind of like whatever they are charging just for the design and the supplies. It doesn't have anything to do with the serving size. Okay, so when you're looking at a table and you want to find b, you have to go all the way backwards until you get to 0 on the x side. And the other side, the y side of the table, is going to give you b. So we would put 15 in for b, and that would give us our function. So it would be f of x equals 2 times x plus 15. The rate of change, they charge $2 per serving, and then they charge like an initial fee of $15 for the design and the supplies. So our final function is f of x equals 2x plus 15. Okay, example 4, write a function to represent the data in the table. So if we look at the table, I think one thing that kind of pops out is like, it looks like we're multiplying by 6 right away. And it's kind of weird because like we have negatives there, but you have to remember, like when you start with a negative number and you multiply by a positive number, your final outcome is still going to be negative. So what I mean by that is like we can see on the x side of the table, it's going up just like 0, 1, 2, 3. So I don't have to do anything funky like I did with the previous example, which is nice. And then the right side of the table is going from -1 to -6. So since I'm like starting with a negative and finishing with a negative, I'm just multiplying by +6, because -1 times +6 would be -6. And then right here, I'm going from -6 to -36, so I'm multiplying by 6 again. And then right here, I'm going from -36 to -216, which if you're not sure what that would be, you can grab a calculator and do -216 divided by -36, and that would give you a +6 also. So every single time we're multiplying by a +6. So when you're multiplying by a consistent number, that would be an exponential function. So it'd be f of x equals a times b to the x, and a was the starting amount, and then b is the like growth factor. So what's kind of nice with this problem compared to the last one is we already know how to find the starting amount. Even though we have a different type of function here, we have like an exponential function. The starting amount when you're looking at a table is going to be wherever there is like x equals 0. That's going to be our starting amount, is that line from the table. It's going to be the f of x or the y side. So that would mean that our starting amount is -1. So to find the starting amount from the table, you have to find where x is equal to 0, but the actual starting value is the f of x or the y that goes with it. So in this case, it's -1. So you'd put -1 in for A. And then the growth factor, that's like, what are we multiplying by each time? We already found that we were multiplying by 6 every single time. So the growth factor is going to be 6. So it'd be f of x equals -1 and then times 6 to the x power. And then that's it. So f of x equals -1 times 6 to the x, and that's as simplified as it can go. Because again, same thing, like we wouldn't be able to multiply the -1 by the 6 until after we simplify this exponent, and we can't because it's just an x, so we don't know what it is and we can't simplify it. Okay, so when you're comparing like kind of tables of linear versus exponential, linear, like if you can identify immediately that you're adding a consistent amount each time to get to the next number, that would be linear. However, on this table, for example, 3, it didn't really look like we were adding a consistent amount because we went from like +20 to +40 to +80. But what was really happening is, this is kind of like the hardest version of this type of problem, is we were skipping some numbers on our table. So if that ever happens, you would compare the slope formulas. So you would go ahead and you would find triangle y over triangle x, change in y over change in x, and compare them all and see if they end up being the same like ours did. They all ended up being 2. Versus if you're looking at a exponential table, you're looking to see if you're multiplying by a constant number the whole time. And then regardless of the type of function, linear versus exponential, to find the starting value, you absolutely have to get to where there's a 0 for x on your table. And then the starting value is going to be the y that goes with it.